So I just extracted a CIF file from Pearson Crystal database. It's not an entirely complicated structure, but it's also not incredibly simple either. I just picked a random one that has, I think, 3 elements, and I'll upload it into VESTA here. And you can see it's not entirely simple. A bunch of atoms in the cubic cell. I think there's about 3, 5, 7, 8, 9, 10, 15. There's nothing with 26 atoms. So the atoms that we're working with, we have aluminum, cesium, and cobalt. And this is going to be PMMA space group. Don't know what structure type. I guess it's, yeah, that might be the structure type. I could read the CIF file actually. Let's see. So it's going to be where is it? Prototype. Okay, yeah. So it's lanthanum, cobalt, aluminum 4. That's structure type. Space group number 51. Yes. Good. So once you're here, you're going to want to export the data. I'll just name it POSCAR, and I'll put into my downloads folder. Save as POSCAR, and it's going to give you the option for fractional or Cartesian coordinates. So we'll stick to fractional here. So now I have it over at the top. Now on MacBook, just renaming it POSCAR.VASP, removing the .VASP won't actually remove it, and for it to be read by VASP, it has to be just POSCAR and nothing else. So I'm not going to even bother renaming it here because it won't carry it over, and I'll show you how that looks like shortly. So let me transfer the file over. Let me make a new directory, demo. I guess what is this? Cerium, cobalt, aluminum 4. So I'll change directory to that demo, and then now I want to transfer over the actual POSCAR. So let me get this going here. Let's see. So this should be, oh, my mistake. So you need to be in another terminal when you transfer files. Okay, right, because I don't need home lab admin, just the DFT. Okay, now we're transferred over and it's here. So to rename it just POSCAR, you just do this, and the MB stands for move. So here we go. We have Al4, cerium, and then cobalt. And the order is that we have Al8, Ce2, cobalt 2, for a total of 12 atoms. And I actually don't know. I haven't ran this structure type in the past, so I don't know what problems we'll go into, if any at all. Hopefully we do run into problems so I can show you how to troubleshoot and go through some things there. So this is going to be my first time using VASPKIT. So I guess let me do the input file generator. Let's do the KPOINTS file. Oh, lost screen. There we go. We'll stick to, what do I usually do? I think I do gamma. Do I usually do gamma? Let me see. So there's okay, I do usually do gamma. There's some, I mean, it doesn't, well, it does matter. if you choose gamma or not. Let me pull this up. 102. So usually you have Moncourse or gamma. That's usually the common things there. I had notes on this. So I believe with the Moncourse pack, you don't want to use that if you're using a hexagonal structure. Gamma, for the most part, is okay. I should check my notes actually, because I just recently decided to do a deep dive into this. So let me see where I actually have everything stored. I think I have it on my VASP HTML. I don't know. Ah, okay. So I do have a website that runs through a start to finish tutorial. It's a little behind. I'm missing some things such as band structure and word function. So that's what this was just an internal note for myself. So gamma centered, offsets are all 0. So this is very much in depth here with various symmetry operations. I don't want to focus on this too much. Use only gamma centered for hexagonal lattice. So that was reverse to what I had said. Energy converges faster with gamma centered than standard Moncourse. Let's see. Mathematically, they converge at the same pace, increasing number of K points. Difference in possible preference of one over the other. Okay. Original sets of Moncourse grids did not include the gamma point. Had a lower symmetry in some cells, particular hexagonal, the maximum symmetry of the cell. Okay. Can be a breaking of symmetries. So I've used gamma pretty much always. I've never used Moncourse yet. Yeah, so it is pretty complicated. There are some more complexities. So I guess, you know, you could assess per the situation, but for the most part, I'm fine with gamma. I do want to go into running both and seeing the difference. That'll be for another day, actually. Anyways, so I'll stick to the gamma scheme. Now here, you're able to assess the accuracy levels, or pick the accuracy levels. 03 to 04 is generally fine, so it'll space out your mesh, and that's just the range at which you're sort of compressing, sort of, but not really. So I'll just select 0.03, and that should be more than fine. Error failed to read. Okay. So it's supposed to be user. Okay. Okay. That's not. Okay. Very good. There we go. Now we could redo this, I guess. CD demo clear. Let's do this one more time. 102, let's get the gamma, 0.03. Hi. Okay. Local VASP PBAL POTCAR. Huh. That's weird. Maybe the tilde is what's giving me a problem here. Okay, I think it might be the tilde. One, 102, 2.03. There we go. We're in the POTCAR file. Now we have INCAR, KPOINTS, POSCAR, and POTCAR. This is the KPOINTS, and this is all symmetric based on the unit cell. So it takes the inverse of that. So POSCAR is good. Right, we import that. Let's view the INCAR. So we have a couple of things here. Electronic relaxation, eye smear. We do need to adjust this to 1 because they are metals. Let's do this at 0.2. SCF convergence. Oh wait. Ionic convergence. 1E minus 0.6 is usually more than 5. Let's do shape, ions, and volume. And I think that should be okay. We don't have to deal with these. Let's put this to false. We don't need the wave bar. Don't need the charge bar. We don't need this. And we don't need this. And precision is fine. Don't need the lock pot. That's for the work function. We'll get that later. Function operators. Okay. Energy cutoff. Now I'm just gonna double check. One of my previous files. I'll just regular and then. Okay. I do end up liking this one better. So this is a template. I think I'm just gonna copy this over, to be honest, because I'm pretty much used to the placement. Yeah, that's what I'm gonna do. Okay, accurate, energy cutoff, good, good, good. Good. Yep. Yep. Similar steps. We're dealing with metal, it's 1, yeah. So, these are the only 2 sections that we need for structure optimizations. Then we undo this later on, we do density of states, this for beta charges and ELFCAR, this for co-HP, phonons, and whatnot. Work function isn't on here, so that'll be another one that we'll have to copy it over when we have the time. We also need, now you may not need this, especially if you're running this locally, because we run with Slurm, so we just have to do this. We set up a job manager. So this is demo optimization. We'll set this to probably around, I'll say 12 hours, because I don't know how long this will take to optimize. I'll do 32 cores. Seems excessive. 2 gigabytes per core seems to be more than okay. I think this one will be demo. What is it? that will be that. And so we redirect the errors here and the output here. Perfect. Actually, this is lab admin. There we go. So this should be set. And now when you use Slurm, it'll be slightly different to actually start your job. So we have everything that we need: KPOINTS, INCAR, POSCAR, POTCAR, INCAR. And I will include detailed notes. I have documentation for that on how to set it all up, and you could even copy and paste the same INCAR file that I have. Let me think here. Ah, yes, okay. Now, usually when you want to run a job, where is it? VASP. Usually when you want to run a job, you'll go over to something like MPI run, right, number of processors for VASP STD, and then whatever name for the output you want. Yeah, so with that, I think it's batch job. Yes, perfect. And now you can view the file. So it's nice to do this immediately to see what happens. If you run into errors in the beginning, you could sort through it and go from there. So this is running pretty quickly. So I guess I'll just stick here for a little bit, at least until it goes through another loop. And then I'll end it, and then I'll go over data accrual next. Yeah, so it's very simple to run everything through, and even analyzing, like, you'll pretty much get like a good grasp of, you know, a routine of navigating through errors. It's very not intuitive per se, but it's really easy to get, you know, a good grasp on things. It's very accessible, so you don't need to be a strict computationalist to know what to do, because there's just a lot of forums where you can sort of assess different things going on. But you know, the point of these tutorials is to avoid scouring the web like I did. So highest band occupied at some K points, include too few bands, increase the parameter n bands. So this tends to be a problem later on when you're doing band structure or anything that uses the WaveCar file, like density of states, or any electronic structure calculations in general. But I'm gonna ignore it because otherwise you'd have to keep the n bands parameter throughout the entirety of it, and I think maybe I should take care of that. Yeah, I might have to. There is a way to determine the number of bands. I actually find that I couldn't find if there was an accurate way to determine this. I actually think I need to update this documentation as well. Let me see what I have written down locally. I think I have a website. Oh, wait. I have it somewhere, but I don't want to. Some sensitive. items in Google Docs. Okay, so this is fine because I don't have the password here. This is completely irrelevant. N bands. Okay. So I could what is it? To kill. I am just gonna cancel it just so I can redo it. What is it to kill the job on Slurm? I have notes, so I'm not entirely lost, thankfully. Just a matter of where do I have it. Is it kill 92? No. Oh, S cancel. And you could also check the energy convergence. So it looks to be fine. And I guess I'll maximize this. I guess 200 is fine. Maybe 250 because it's going pretty quick. Now end bands. Let's actually figure out how to calculate this. So, VASP also has documentation on how to calculate this, but whenever I try to calculate it, it's not correct. I still get too few, and I end up adding 10, and it's fine. Oh. 66 electrons and 12 ions. Now if we go here, number of electrons is 66. Hold on, I gotta write this down somewhere else. Max at number of electrons divided by 2. Okay. Plus number of ions divided by 2. So 33 plus 6. And then comma, number of electrons times 0.6. Excuse me. How does this... Why is there a comma? Yeah, this is why it never works, I think. Okay. Oh, some transition metals open up shells much larger number, up to... Okay, so we'll work with that. We'll do number of electrons divided by 2, 33, plus 2 times the number of ions, which is 12 plus 33, 24, gives you 57. So, go back here. 57 is what we want to do minimum. So I'll just crank it up to, I don't know, 65 should be more than okay. We'll run SBash job again. Now we could view it again and see what happens. And we shouldn't be running into any errors this time around. But we'll see. But it's good we are running through the errors. So, looks like it's converging fine. That's very good. As it, the difference in energy goes down to very small numbers, we're getting the minus -0.08, so it's moving on to the next loop. And d epsilon, same thing. Rho mean squared is decreasing, so these are all good signs, and they point towards overall convergence, as well as with the same energy slightly decreasing. We'll just let that keep running and go from there. So, overall iterations that's doing, right, we have 25 steps for the first loop, 14 for the second, 14 for the third. I guess this should be, yep, 16. So you'll see as well a decreasing number of steps to reach the electronic convergence. So all these ones are individual ionic, and then the entire loop will be the electronic over at the end, I think, mostly. Alright, so we've reached our required accuracy. It stops structural energy minimization. So, do Control Z here to get rid of that command. So, you want to copy the concar to the POSCAR, and this will give you your new structurally optimized coordinates. Pass it off to your POSCAR file, and you just repeat it, which is a good practice. I usually do 3 times. Make sure you really get the lowest energy position, and then we do tail F out again, and we just do the same thing. There we go, considerably faster than the last time. Copy concar, that's batch job. Let's tail it. What does it say? Profile. Okay, you should redo it. Interesting. You know why? Because we have the wave bar, don't we? Yeah, okay. Let's redo this and see what happens. Well, S-bands is 72. Weird. Usually deleting all of the other files that you don't need. This one, okay. Do the ground state calculation. Okay. Let's see. I'm just gonna stick to it and see what happens. Shouldn't really give me a problem, but I guess we'll see. Just do it one more time. Probably overkill at this point. it should converge in like 3 loops now at this point. There we go. We'll do one more copy, INCAR POSCAR, and you can see what that looks like. Here. So now we can view the POSCAR for our optimized X, Y, Z, optimized unit cell coordinates A, B, C, or X, Y, Z. No other parameters here, no angles, no alpha, beta, gamma angles to take care of, because this is rectangular. Yeah, and then you just get your final energy there, and that pretty much is it. And that concludes the ground structure, ground state calculation, optimization, and we'll do electronic structures in the next video. We'll start off with density of states, do LaCoAl₄-type, band structure, the whole 9 yards. And that's it. Thank you for tuning in.